Okay, here's a reaction we've seen before. It's just a little bit different than with the way that we've seen it. This is the reverse reaction of the way that we saw it. So we saw it in terms of an elimination reaction where concentrated acid added to an alcohol will form an alkene. Now we have dilute acid added to an alkene that'll form an alcohol. So we got to remember that by and large, acid-base reactions are equilibriums, and so they go both ways. And which way they go depends on sort of the concentration of the reactants. Dilute acid has lots of water. Water is one of the other. If I were to sort of write the reaction in general chemistry terms, water is one of the other reactants, and so having a dilute acid forces the reaction in that direction towards the alcohol. So it's actually just asking us to do a mechanism, and we've seen this reaction before. We've done it in reverse. We're just going to go back the other direction. So it's still going to form, it's going to start off with a proton transfer to the double bond to form a carbocation. Now, what's going to happen here is that it's going to form a secondary carbocation. And if you notice, the OH has added to a position that's tertiary. And it also looks like a methyl group has moved around. So there's going to have been some sort of rearrangement that occurred in this process. And this is where it occurs. So this is a secondary carbocation. And the secondary carbocation is not as favorable as a tertiary. And so you can get a tertiary carbocation if you just do an alkyl shift, and that alkyl shift will provide the ability to form a tertiary carbocation. And now the water can come along and attack that location. And we'll get another intermediate that involves having a water attached. And another water will have to come along finally to do the proton transfer. Is catalytic in the sense that the acid reforms. And that's what gets us our product. Okay.